So we are provided with three distinct real numbers a, b and c, and magnitude wise they are all less than 1, meaning the value of a must lie between -1 and +1. Similarly for b and c, its magnitude lies between -1 and +1. Now we need to show that there are three numbers x, y and z. They are in harmonic progression provided the values of x, y and z are given by this particular series. So let's try to understand this problem. Okay, so here we are given x equals to summation of a raised to the power of n, where the index n runs from 0 to infinity. So let's expand it. So when we put n equals to 0, we'll get the first term. So that's a raised to the power of 0. Then for the next term, we put n equals to 1. So we get a raised to the power of 1. So that's simply 1. Then we have a squared. Next will be a cubed. Then a raised to the power of 4, and this goes on to infinity. Now, clearly, this is a geometric series. Here, the first term, which is a raised to the power of 0, that's simply 1. The first term is 1, and the common ratio, we can define the common ratio here. So here, let's say that this is the first term. And we have r, so this is going to be the common ratio. So we can find out the common ratio by taking the second term and dividing by the first term. A divided by 1, so that's going to be equals to a. So our first term is 1. Now since this is a geometric series, an infinite geometric series, then we can find out the sum of an infinite geometric series by using the form that sum up to infinite series is given by the first term divided by 1 minus the common ratio r. So if we substitute the values, so a value is 1, and we have 1 over 1 minus a. So this is going to be the value of this infinite geometric series. So that's 1 over 1 minus a. So that's the value of x. Right. So what we'll do, let's find out a from here. So we have 1 minus a equals to 1 over x, or simply a equals to 1 minus 1 over x. Fine. Now we'll go to the next series. So we have the next infinite series of y. So y is summation b raised to the power of n, with n going from 0 to infinity. So when we expand it, we also get 1 plus b squared, and this goes all the way up to infinity. And the sum up to infinite series will be the first term divided by 1 minus the common ratio. So in this case, the common ratio is going to be b. So that means we now have the value y equals to 1 over 1 minus b, such that if we isolate b, the b will be 1 minus 1 over x. Fine. Then finally we have z, which is also expressed in terms of a summation c raised to the power of n. So we have n going from 0 to infinity, and that's on expansion gives us 1 plus c squared plus c cubed all the way up to infinity, and this sum is given by 1 over 1 minus c. So isolating c, we get c will be equals to 1 minus 1 over z. Fine. So we have found out the value of a, b and c. Now in the problem, it's given here that a, b, c are three distinct real numbers, and these numbers are in arithmetic progression. Since a, b, c are in arithmetic progression, so we can say that in place of a, we have 1 minus 1 over x. We have already obtained this value. Then we have b can be replaced with 1 over 1 minus y. My mistake, so this is 1 over y. And then for c, in place of c, we can replace it with 1 minus 1 over z. So these three numbers are in arithmetic progression. Now what we'll do, we'll subtract 1 from each of the terms. On subtraction, we have -1 over x, -1 over y, -1 over z. So these are in arithmetic progression. So subtraction does not affect the arithmetic progression. And finally, we're going to multiply each terms with -1. So we have 1 over x, comma 1 over y, comma 1 over z. So these three numbers are in arithmetic progression as well. Now, if they are in arithmetic progression, then the reciprocal of each of the terms, we have x, y, and z, and these three terms are going to be in harmonic progression. So hence, we have successfully showed that the x, y, z are in harmonic progression.